Welcome again to the AIA structural exam modules. This is module 5. We're going to look at trusses today. So trusses, let's talk a little bit about trusses and understand exactly what a truss is. A truss has a couple of unique qualities that makes it different from any other type of structure. The most important thing is that all of the joints in a truss are pinned joints. And so let's see exactly what that means. Here's a truss, very simple truss. These are used in bridges, in roof structures all the time. And all of these joints are pinned. So if I have my truss supported here at two endpoints and I apply a load, the deflected shape of the truss will look something like this. It will bend downward just like a beam, and the bottom members will go into tension. The top chords will go into compression. Every truss member is referred to as a chord that goes diagonally. So this member here, and I'll put some labels on here so we can talk, A, B, C, D, E, and F. So for chord, for example, E, C, the load is purely axial. Every truss has only axial load, which means it's either tension or compression. Tension meaning that it extends, compression means that it compresses. A truss behaves similar to a beam, just like in a beam. If I was to make this entire thing out of a beam and have it simply supported and apply a load, just like a beam will deflect, a truss does the same thing. The only thing that we've done in the truss is we've cut out the elements of the beam that are unnecessary. We've taken out elements in here that are costing a lot of materials, and we've tried to make it efficient version of a beam. That's what a truss is in my rather simplified sketch here. In every beam there's an embedded truss where you have diagonal members. In this case we may have double diagonal members. So every joint in a truss is a pinned connection. That means that there is no moment. I'm going to label this sheet as sheet number 1 for module 5. Let's take a look at the next section to understand what we mean by a pinned connection. So a pinned connection means that there is no moment. It means that there is, it does not mean that there's no rotation. You can have rotation, but you have no moment resistance. So if I have a truss connection, and here's what a real truss connection may look like. It may look something like this. It may have a gusset plate with several members coming in. Here's what a real truss connection could be detailed as, just approximately. And so you may have bolts, you may have even welds. But when you compare a truss connection like this with the length of these members, this does not provide sufficient moment resistance. And so we treat it as being pinned. It's an approximation. It doesn't mean that the truss is purely pinned and perfectly pinned. It just means that it's an approximation. Approximation to the real world design. So let's take a look at how we solve these. We have two methods that we can use for solving a truss. Let me label this last page. This was page 2. Let's go to page 3. And let's take a look at a real truss problem. Make it a very simple truss problem. We'll have one bay with a cross framing member, one diagonal tension member. And we'll label these points here. We'll make it simply supported so that it's statically determinate. 3 kips over here, 9 kips over here, 12 kips, and 1 diagonal tension member. All the joints are pinned. We'll label the lower joints with lowercase letters, A, B, C, and D. And we'll label the upper points capital B and capital C. And let's put some dimensions on here. "15 feet. And we'll make this 20 feet, 20 feet, and 20 feet. So the slope of my triangles are a ratio of 3 to 4 to 5. So we have 3 to 4 to 5. So the first thing we've got to do is calculate reactions. That's usually the first step. In this case, it's not as complicated as it looks because my truss is actually loaded symmetrically. My total load here along this line is 9 plus 3 is 12 kips, and my load here is 12 kips, and they're perfectly symmetrical. So actually, I can just, by looking at that, by deduction, write down my reactions. Now, not every problem is going to be that simple, but for this one, it's pretty straightforward. And you want to take advantage of all the symmetry that you can. So we have two ways to solve these. There's the method of joints. There's the method of sections. The method of joints is taking a free body diagram of each joint and working your way throughout the entire truss. The method of sections is to cut sections as appropriate in order to solve the loads. Let's start with the method of joints, and let's take a look at joint A. So joint A, we have an upward reaction of 12 kips, and we have two members, AB, A lowercase b, and A capital B. And I've drawn them both in tension just for simplification for now, and I'll show you how we can determine which one is in tension and which one is in compression. I can tell you right now, just by looking at this diagram, that this is going to be going in the opposite direction. And the reason is that if we look at the component, this is broken up into two components. Let's look at the vector forces. If we look at the vector forces split between this top chord force and this bottom reaction force, we can see from joint A that if we have 12 kips going upward, the top force has to be going down because its component going down has to balance the 12 kips, which immediately tells us that this component has to be going to the left. So AB, A capital B, in the y direction has to balance the 12 kips. And that y component here, which has to balance this component, automatically tells us that this component of the AB chord force has to be going to the left, which tells us that this force on the lower chord, AB, is going to the right. So when the force is coming into the joint, This tells us that this is in compression. This tells us that this is in tension because it's pulling. It's pulling away from the joint. So if ABY is equal to 12 kips, and then using some basic geometry here, that if we have a 3 to 4 to 5 triangle, it tells us that ABY is equal to 3/5 AB. Therefore, AB is 5/3 times 12. 3 goes into that 4, that's 20 kips. And that's in compression. And if AB is 20 kips, then ABX, which is the X component, will be 4/5 of AB, which is 4/5 of 20, which is going to be 16 kips. No. So the ABX, which is geometrically 4/5 of AB, and the way we know that is from the geometry of the triangles, just using trig, the ratio of the horizontal to the hypotenuse. 4/5 of 20, then we get 16 kips. And that 16 kips going in this direction for ABX means that AB, A lowercase b, is equal to the X component of ABX. So that's 16 kips, and that will be in tension. So right away we've solved for this chord force, which is 16 kips, tension, 20 kips, tension. And because the truss is loaded symmetrically, we automatically know that the force over here will be 16 kips in tension, 20 kips in compression. So we've kind of already solved half of the truss. Let's take a look at joint B, because joint B is a fairly straightforward joint to solve. And why am I picking on joint B? You'll see in a moment, because joint B has 2 chord forces which are in the X direction and 1 vertical truss member force. So let's look at joint B. This will be sheet number 5. So let's look at joint B. So joint B, we know that AB is a tension force, so that has to be pulling 16 kips. We know that we have a vertical load of 9 kips, and we will be able to tell automatically that the load BC has to be going to the right, and we know that lowercase bb has to be going up. How do we know that? Because some of the forces in the X direction has to be 0, some of the forces in the Y direction has to be 0. Some of the forces in the X direction tells us that BC has to equal 16 kips, which means that that's in tension. So now going back to our truss, 16 kips in tension has to be on the bottom chord. So you can see that our truss has 16 kips of tensile load across the bottom chord all the way across. Some of the forces in the Y direction tells us that B capital B must equal 9 kips, and that has to be in tension also now. Not a compression. That has to be in tension because this is pulling. So this chord, because this is extending down, if we drew the deflected shape would look like this. And so this chord is getting pulled. So this 9 kips is in tension. So now we have only 3 members left, and they shouldn't be too difficult to solve. Let's take a look at joint B, capital B. So joint B, we have 20 kips in compression. So that's 20 kips is coming in from here. That's from the chord force A capital B. That's coming in that direction. and we have 3 kips downward load coming from the load up on top. We have 9 kips in tension pulling down. We've already solved for that. And so what are we missing? We have BC, which we don't know the direction of yet, but we can figure it out with a little bit of deduction, and then we have BC. So we have capital BC, and we have capital B, lowercase c. So how can we figure out which force is going in which direction? In this case, because the chord running diagonally here, from looking at the deflected shape, will be extending. That diagonal chord is going to be in tension. The top chord is going to be in compression, and I'll prove that to you in a moment. But if we draw it in there for now, that's going to be the final load diagram. The other way you can also tell is you can sum the forces in the y direction. That's a fairly simple way to solve this because BC cancels out. The horizontal chord force cancels out. Let's take a look at that calculation. So this is sheet number 6. What are the slope diagram here? Well, same slope diagram as we had before. It's going to be 3 to 4 to 5, so it's 3 to 4 to 5 triangle. And so if we sum the forces in the y direction, we will have minus 3 plus 20 times 3/5 minus 9, and then minus b lowercase c y component equal to 0. So that's minus 3 plus 5 goes into that 4, that's plus 12 minus 9 minus BC in the y direction must equal 0. And something unique happens on this truss. This cancels out. We have minus 12 plus 12, which becomes 0, minus BCY equals 0 tells us that BCY is 0, which tells us that BC is 0, which means that in the end analysis, my truss is having a 0 axial tension load here, at least on calculation-wise. And if that's a 0 tension load in my analysis, that tells me that my capital BC up on the top chord is going to be in compression. And so let's do the calculation for that. That's some of the forces in the x direction. And some of the forces in the x direction, we're going to have to the right being positive. The 9 and the 3 don't enter into play. We have plus 20 kips, and we have to have BC going in the opposite direction. So we have minus BC, or excuse me, plus 20 times the ratio using the triangle, which will be 4/5. So that's 4/5 times the 20 minus BCX equal to 0, which tells us that BC x component is going to be 4/5 times 20, which is 16 kips in compression. So going back to our truss, this is 16 kips in compression. This is 9 kips in tension. And this load here, since this is 0, and we know that this is 12, we can immediately see is going to be 12 kips in tension. And how can I see that? Let's take a look at joint C. Let's take a look at joint C. Joint C is again becomes a rather simplified joint because that diagonal tension member is a 0 load. So I am on sheet number 7. So let's take a look at joint C. Lowercase c. So the lowercase c, we have 12 kips going down. We have 16 kips in tension on the left-hand side, balanced by 16 kips in tension on the right-hand side. We have a chord load, which is 0, which we calculated. That was the capital BC, which we calculate as being 0. So that's not doing anything. So that tells us automatically that this force here has to be going up because of some of the forces in the y direction equal to 0. And if we sum that, that's the chord load, lowercase capital C, has to equal 12 kips. There's no other way about it. So this has to equal 12 kips, and that has to be in tension. And that gives us this load. And then we're done. We'll do another example using method of sections. That concludes this module. Thank you.